this ship is taking on water. And that is not a mistake. In fact, if this ship were completely sealed, it would be more dangerous than safe. That sounds wrong. Because everyone learns the same thing. Water is the enemy of ships. Water inside means sinking. End of story. But modern ships are not designed to be fully sealed. They never were. And in the next minutes, you're going to understand why one of the most important safety principles in naval engineering is allowing water to enter the ship in very specific ways. If you enjoy understanding why massive systems survive by doing the opposite of what we expect, subscribe to the channel. This is Critical Limits. Let's start with the belief almost everyone has. A ship floats because it keeps water out. So the better sealed it is, the safer it must be. That feels logical. But ships don't fail because water exists. They fail because water goes where it shouldn't, too fast in the wrong place without control. A perfectly sealed ship is not a strong ship. It's a rigid one. And rigidity is one of the most dangerous things a structure can have at sea. The ocean is not static. Waves lift one part of the ship while another part is unsupported. Cargo shifts. Temperatures change. Steel expands and contracts. A ship is constantly bending, twisting, and flexing. If you seal everything perfectly, pressure has nowhere to go. Think about a plastic bottle filled with air. As pressure increases, the bottle deforms. If it can't deform enough, it ruptures. Ships work the same way, just on a massive scale. So engineers design ships to breathe. Not literally, but structurally. Let's talk about compartments. Modern ships are divided into watertight compartments. Not one big sealed box, but many smaller ones. If water enters one compartment, it doesn't automatically spread to the rest of the ship. This is intentional. Controlled flooding is safer than uncontrolled pressure. In some cases, allowing a compartment to flood actually stabilizes the ship. Water adds weight, but it also lowers the center of gravity. A lower center of gravity increases stability. This is why ballast tanks exist. Ballast tanks are designed to fill with water on purpose. When a ship is empty or lightly loaded, ballast water is added to keep it stable. When it's fully loaded, ballast water is pumped out. So right away, we see something counterintuitive. Ships are designed to carry water inside them as part of normal operation. Now let's go deeper. Why not seal everything and only allow water into ballast tanks? Because ships are not solid objects. They are long, flexible structures. When a wave lifts the bow and the stern is unsupported, the ship bends downward in the middle. This is called sagging. When the middle is lifted and the ends are unsupported, the ship bends upward. This is called hogging. This happens constantly. If the hull were perfectly sealed and rigid, these forces would concentrate stress in specific points. Steel doesn't like concentrated stress. It cracks. Instead, ships are designed to distribute stress gradually. Tiny gaps, drainage paths, expansion allowances. All of these let the structure move without tearing itself apart. Now imagine a ship that is completely airtight and watertight. As it bends, internal pressure changes. Air compresses. Water shifts. Pressure builds where it shouldn't. That pressure pushes outward on the hull. So instead of only dealing with ocean forces from the outside, the ship is now fighting itself from the inside. This is why ships are not fully sealed. They need controlled paths for pressure equalization. This brings us to something most people don't know. The deck of a ship is not meant to be watertight in the way people imagine. Rainwater is expected to land on deck. Seawater is expected to splash over. Decks are designed with scuppers, drainage openings that let water flow off. Why? Because water on deck is dangerous. A thin layer of water moving side to side creates a free surface effect. The free surface effect is when liquid shifts inside a container, amplifying instability. That's why partially filled tanks are more dangerous than full ones. So ships actively remove water from decks and guide it away in controlled paths. Again, not sealing, managing. Now let's talk about emergencies. When a ship takes damage, the goal is not to keep every drop of water out. The goal is to slow water ingress and control where it goes. This buys time. Time to redistribute weight, time to pump water, time to stabilize. A ship that is perfectly sealed but suddenly breached fails catastrophically. A ship that is designed to accept limited flooding fails gradually. Gradual failure is survivable. This philosophy appears everywhere in engineering. Airplanes bend instead of snapping. Bridges flex instead of cracking. Ships flood instead of exploding. Now let's address a common fear. If ships allow water inside, why don't they just sink slowly over time? Because buoyancy is about displacement, not dryness. A ship floats because it displaces a volume of water equal to its weight. As long as the ship displaces enough water, it floats, even if parts of it are flooded. Submarines are the extreme example. They are literally designed to flood themselves entirely and still remain controlled. So flooding alone is not the enemy. Uncontrolled flooding is. This is why compartment design is so critical. Engine rooms, cargo holds, fuel tanks, ballast tanks, all are isolated. If one floods, others compensate. This is also why doors between compartments are so heavy and sometimes kept closed. Not because the ship must be sealed forever, but because flooding must be localized. Now let's talk about corrosion. Salt water is brutal to steel. You might think sealing everything would prevent corrosion. But trapped moisture is worse than exposed moisture. If water gets into a sealed space and cannot evaporate or drain, corrosion accelerates. Ships are designed to allow ventilation, drainage, and inspection. Again, controlled exposure beats trapped danger. Now let's zoom out. Why does this topic matter? Because many famous ship failures were not caused by too much water, but by poor control of water. The Titanic did not sink because water touched steel. It sank because multiple compartments flooded faster than the ship could compensate. Modern ships are built with lessons learned from these failures. They are less about perfection and more about resilience. A resilient system expects failure and survives it. A perfect system breaks the moment reality disagrees. This is the core idea behind why ships are never fully sealed. They are designed to live in an environment that never stops pushing. So they must yield, adapt, and manage forces, not resist them absolutely. This brings us to a subtle but important psychological point. People trust ships because they look solid: steel walls, massive hulls, thick plates. But safety doesn't come from thickness alone. It comes from understanding where strength becomes a liability. A ship that refuses to let water in will eventually let water in violently. A ship that accepts water on its own terms survives longer. That's not weakness, that's control. And this idea shows up everywhere in engineering. The strongest systems are not the ones that fight reality. They are the ones that cooperate with it. So the next time you see a massive ship crossing the ocean, remember this. It is not sealed shut. It is breathing, draining, flexing, adjusting, every second. Not despite the ocean, but because of it.